So take your seats, buckle up for middle boxes and network functions. The bane of the existence of the IETF. So this session has 3 talks. Interesting mix of things. The common theme, of course, is what happens in between the people who are trying to get useful work done by things in the middle that are trying to help them, help in quotes. First talk is limitless HTTP in an HTTPS world, where the authors try to infer semantics of HTTP operations by observing traffic without having to decrypt it. The authors are Blake Anderson, Andrew Chi, Scott Dunlop, and Dave McGrew. And the talk's going to be given by Blake Anderson, who's a software engineer at Cisco, who unintentionally shared with me that he's a reformed physicist like me. A reformed physicist like me.
All right, thanks. Yeah, so I'll just jump into it. So the goal of this work, there's like 2 goals really, but the specific goal of the work that I'm going to be going over in this talk is that given a stream of TLS application data records, we want to be able to infer which records have which specific HTTP frames, the frame types, and then for the subset of those application records that contain headers frames, we want to be able to make even more detailed inferences about the HTTP headers that are inside that frame. And in some cases, we want to be able to say what were the actual values of those HTTP headers. And a higher level goal, which I'm not going to really spend too much time on, but given those inferences, so given the fact that we can annotate a TLS session with this information about where the headers are and what those specific HTTP fields and values for those headers, what they actually are, how can we use this? And in the original CodeSpy paper that this talk is based on, we presented it in 2 ways, where what can a defender do and what can an attacker do? From the point of view of the attacker, it's mostly centered around website fingerprinting. From the point of view of the defender, it's mostly centered around identifying malicious communication, malicious websites, and doing things like identifying data exfiltration by matching the sizes of the data objects downloaded or uploaded versus something that's in a contextual database. And so the motivating factor for all of this is what many enterprises look like today. It's very generic, cartoonish picture, but we have some set of clients that are internal. They want to talk to the internet, so there's a man-in-the-middle proxy in between those 2 that will decrypt the traffic and make sure that it's good and then send it on its way. And basically, this work is saying if we eliminate the man-in-the-middle box and we want to do how many of those features can we get away with by passively observing the TLS traffic? Can we ensure that there's not malicious communication, that sensitive data is not leaving the network, with the hope that if we can get close enough, then we wouldn't have to rely on man-in-the-middle boxes, at least for all the functions. And so to level set, after the TLS handshake, this is more or less what we see, a series of application data records between the client and the server. And interestingly, when we actually decrypt that and look at what's underneath, we could have HTTP1, HTTP2. If it's HTTP2, we have a series of all these different frame types where some of it's setting up the connection, and then it's the client is actually requesting some data from the server in a headers frame, and then there's a little bit more setup, and finally the server sends its headers response and the data. So a big part of this work was building out the infrastructure to build the data sets that correlate, this view that we can passively observe on the wire with a view that has, this detailed data, the TLS application data records that are annotated with the information that we want to be able to infer. So, it's like 99% of what we did was, building out those training data sets. And then the last 1% was some light machine learning. And so we started by, obviously we needed the TLS key material. And, interesting, Andrew Chi did most of this work. And I asked him, given a memory dump, go find all of the TLS master secrets and do all these like entropy type things. And I thought it was going to be like a summer-long project. He came back that afternoon and was like, oh, here's like 3 or 4 regular expressions that will get you all of this data. And it worked out really well. So yeah, he defined a couple of regular expressions for S-channel, OpenSSL, and NSS, which gave us the majority of what we needed. So, we took that and we started transitioning it. So to extract the key material, we do one of 2 things. So for Firefox and Chrome, we just use the SSL keylog file environment variable. Obviously, it's a lot easier. And then as a more general approach, given a memory dump of either a process or a virtual machine, we will use all of the regular expressions to extract those master secrets. And Scott Dunlop took some of Andrew's work and tuned it and was able to get it to run in about 400 milliseconds for a 1 gigabyte memory dump, which is what we did for the standard setup for the malware analysis sandbox, which I'll get to in a minute. And from there, we had a Python program that we wrote that would take the master secrets and Tor AES keys, and it goes through and decrypts all of the traffic so that we get a nice JSON file that says application data record contains these HTTP headers. And then for Tor, it was an interesting, the code is actually really ugly. So the Tor, the outside layer is normal TLS application data records. And when you decrypt that, you start to see all of the Tor cells. In this case, it's the relay data cell. And so here you need to maintain a list of all of the AES keys, and you need to know the proper order, which we just brute force. And then finally, we'll get the TLS protocol, which again, we need to decrypt that with the TLS master secret to get that association between the HTTP headers and frame types that we care about and the outside TLS application data record. And we had 2 main avenues to get this data. So one of them was a decryption lab that we set up with Chrome, Firefox, and the Tor browser, where we would just, we got the Alexa top 1,000 websites and just pinged each one of them and collected, all of the initial sessions and all of the ancillary sessions that happen, along with all of the key material. So either SSL keylog for Firefox or Chrome. For Tor browser, we took memory snapshots every 2 seconds, which seemed like a pretty good trade-off. We got the majority of the both the AES keys for Tor and the TLS master secrets for the Firefox processes. So the malware sandbox is the other set of experiments, or the other large data set that we used. And this is a production malware analysis sandbox running Windows 7 and Windows 10. Samples were allowed to run for 5 minutes. And then at the end of the 5-minute run, the memory dump from that virtual machine was post-processed to try to extract all of the TLS master secrets from major TLS libraries. And you would think that approach would work poorly because, at least initially, we thought that the TLS master secrets would be mostly zeroized. It turned out that wasn't the case, and it's right around 80% of the TLS sessions. And that's, 80% of the samples and 80% of the TLS sessions, so samples and sessions are relatively close to each other, but we could decrypt the majority of the data, so we were able to actually get the key material for most of the sessions. And then we ended up with 4 main data sets, so Firefox and Chrome, Tor, and malware. So the Firefox, Chrome, and Tor data sets are slightly different from the malware data set, and the biggest sense is that they're all relatively homogeneous. So all Firefox connections are obviously going from the same version of Firefox. The malware data set, on the other hand, has a wide variety of different TLS libraries and applications. The standard Windows S channel, types of TLS connections were by far the most prevalent. They were about 60% of the data set, and then there was kind of a long tail between, a long tail to finish it off. And right, so to recap, we have our data sets. They're well labeled. We're able to associate the encrypted data features that we would see on the wire with the unencrypted data features that we want to infer. But we still need that extra step of like what actual data features are we going to feed into our machine learning algorithm. And after some trial and error, not too much trial and error, we kind of settled on this set of data features. And the important thing here is that there is a sense of locality for each data feature. So if we're trying to identify HTTP headers for a specific application data record, we would take the number of packets in that application data record and other things like TCP push flags and packet sizes in bytes. But we would also take the set of data features from the previous 5 application data records. And so this could be things that are in the actual handshake. And then the TLS records from the following 5. And they could be 0 if it's at the end of the session. And that locality really does help. And the other thing that really helped was the iterative classification. So the assumption here is that all of these headers are kind of interdependent. So if we know something about the HTTP request, that gives us a lot of information about the HTTP response. So what we do is we make a single pass where we identify the HTTP frame types and make an initial guess at all of the header fields and values. And then we refine all of those guesses by including in the feature set the guesses from the previous round. Right, so to talk about the actual inferences that we wanted to make. So the data sets that we collected, at least for the Chrome, Firefox, and Tor browsers, they had limited variability in the requests. So a lot of the results in the paper are more server oriented. So that was one of the limitations. And the other thing is that we're not claiming to do something like identifying the exact value of a cookie field, because it's probably not exactly possible, at least with these methods. So we set up our classification into 2 broad sets. So we have a set of multi-class classification problems, and I think these are the 5 that are listed here. So things like the method, the response, the content type, and the actual server field were multi-class classification problems where we're trying to identify a specific value, so a specific JavaScript versus image. In addition to these, we had a set of binary classification problems, and here the intuition is that the fact that there's a referrer field present in an HTTP request gives us some amount of information. Or the fact that there was a a cookie field, yeah. So a cookie field also gives you some amount of information, and you can actually get it's difficult to get the actual values for these, but determining their presence was significantly easier for these techniques. All right, so I apologize. This is a little bit of an overloaded slide. This is kind of summarizing all of the results that we did. We broke it out from HTTP 1.1 and HTTP 2, and there were two main sets of experiments. So there was one experiment where we divided the training and the testing set by weeks. So we took 1 week of data to train, and then we took the second week of data to test. And the other set of experiments used an SNI-based split, where no two SNIs were in both the training and the test set, and they were relatively even. There are many interesting observations like in this data set. One of them being that we can do a really good job of identifying message types. So we can, with relatively high confidence, we can say, this packet has a HTTP request versus data versus ping frame, etc. The other interesting thing is that even for some of the more difficult multi-class classification problems like server identification, which actually isn't on this, it's in the paper, we're able to do surprisingly well, especially in the non-SNI-based data set. So if we were doing time-based splits, which it is reasonable, especially for some of the servers that don't really change that much. We can do a pretty good job of identifying the different types of web servers. And a really good example that we had was where we opened a session to like gmail.com, and there were several different servers in a single connection to gmail.com, and we were able to identify each of them. And content types actually have specific results on content types. So these are all confusion matrices. So a perfect algorithm would get everything in the diagonal. So that's what we want. For the cases of Chrome and Firefox, we're able to do a pretty good job of identifying the content types. And this is a heavily imbalanced data set. So, if you've ever looked at a lot of this traffic, which I'm sure all of you have, images are, definitely in an order of magnitude more than something like JSON. So, from a machine learning perspective, imbalanced data sets make things pretty difficult. But we were able to do a pretty good job relatively evenly across the data sets, except for the Tor data, which more or less overfit everything to image. And again, that was mostly because Tor does, I guess there's two things. So Tor does fixed length messages, and it does a lot of multiplexing. The fixed length messages and some of the side experiments that we did had relatively little impact on these techniques. The multiplexing, on the other hand, had a huge impact. So multiplexing many sessions over a single section is probably the most valuable defense to these type of techniques. So quick conclusions. By far the most important part of all of these experiments was building the ground truth data sets. So if you're willing to invest a lot of time into coming up with a very varied representative data set that can actually make that can actually link the things that you care about, so that the application data records and the unencrypted HTTP headers, actually defining the machine learning algorithms to take advantage of that is relatively easy. Like I just said, fixed length records, they don't make these techniques work better, obviously. But really the biggest thing was the multiplexing in terms of a deterrent. And then finally, so the results are most certainly client dependent. In the paper, we looked at training the classifier on Firefox data and testing on Chrome data and vice versa. And it does relatively poorly. So it's definitely leveraging some of the artifacts of the specific browser. So to actually make these techniques efficient and like production, you would need to have like a pre-processing step where you do something like TLS fingerprinting to identify the actual TLS library in use, and then bring in the right model to identify these features. That's it.
Great. Questions, folks, please come to the mics.
Hi, Chris Wood. Thank you for bringing this research to the ANRW. I think it's really great. I had a question about the mitigations that you talked about at the end, in particular the fixed length record possibility. Did you do any experiments with perhaps what is a, it all depends on a lot of conditions, a lot of variables, what is a good size for that fixed length, and whether or not it needs to be applied in both directions the same way, like from client to server and server to client? Or did you just take like Tor's implementation or Tor's fixed length and infer from that?
So I just took Tor's fixed length, and to give a little more intuition, I did some relatively artificial experiments where I created new data sets where each TLS Tor session only included one TLS connection. So more or less like you would see from TLS on the wire. And in those cases, Tor did not give you anywhere near the same protections as the multiplexing case. So that's where that intuition comes from. I haven't looked very much at varying that size of fixed length records.
All right, thank you.
Hi, Pat McManus. Thanks for doing this. This is really interesting. I'm curious, sort of just from the last slide where you talked about the level of fingerprinting, being used to classify the data as the trainer, and then where you can kind of, apply the results. And the emphasis on the client side, sender is doing like the bulk of the sending. Why don't you think that has a bigger sort of influence on how that happens? I mean, some of the things you determine are, basically client fields, the method and whatever, but like the content type, for instance, comes from the other side.
Yeah. So, sorry. The interesting thing is if we were, I don't know exactly how to say this, but we could throw enough. I hate the explanation of like throwing data at it. So like the malware case is a really good example where it encompasses a large number of clients. And if they're relatively well represented, then it can do a pretty good job of identifying it. That's what's happening on the server end. So the fact that we have a relatively distributed set of servers in the training database, the server specification actually doesn't influence the model as much. On the other hand, if we have like Chrome and Firefox, we train just on Chrome, it will do a bad job at classifying on Firefox. If we do something like the malware data set, where we get really large number of examples from every possible client and then train the machine learning algorithm, it would probably have performance similar to that of the malware data set, which the malware data set's a little worse than the Chrome and Firefox specific data sets, but it does all right. And I think we wouldn't want, it would be difficult to create a system that had a reasonable number of false positives if we both ignore any kind of domain knowledge on the client side and the server side. So, definitely in these experiments, we picked to ignore things about the server and just let the data take care of that. I think doing both of them would, it leads to slightly reduced results based, like, as you can see in the malware data, and it would be, I guess at the end of the day, it would be better if you had specific models for each client because that would improve performance, but it's not necessary.
So one more question, Lois. Yeah.
Thanks. Wes Hardiker, ISI. So somebody on the internet and in the IETF said something wrong, so I naturally wanted to correct them. And I've been thinking about collecting a bunch of data like this, actually, and started doing this last week. And then to find out that you've pretty much done all the work for me, so I really appreciate that. Fantastic work. Did you mention, I don't think you mentioned if you're releasing any elements of it, either data or models or tools or code or anything?
So it was our original intention to release everything.
That's about the answer I expected.
And actually, I'm probably at fault more than anyone. I think it would be great to send me an email and remind me. There's very little that's actually sensitive in this data set since I collected it all on a virtual machine. And most of the tools that we wrote, I think, could definitely be open source. I don't think there's that much that's sensitive with them. I would need to talk definitely about the tools. The data itself would probably be easier to open source. I definitely would want to do that. Email me and remind me.
All right. Thank you, Blake. Everybody. So our next talk is on flexible middle box implementation in user space. The authors are Corinne Edeline, Justin Lurman, Cyril Soldani, and Benoit Donnet from the University of Liège. And talk will be given by Corinne Edeline. We all set? It's missing the images. Oh, that's not good. Okay. Whew. Let's hope the battery does. You'll talk fast. We're worried that his battery might die because his AC adapter is a little flaky. So there'll be some motivation to talk fast.
Okay.
Take it away. Yeah. Hang on. Is that better? It's interesting. It's bright enough on this monitor. Okay. So Corinne's a PhD student at the University of Liège and works on middle box classification, impact on transport protocols, published a bunch of stuff, and will be defending his thesis later this year. So come back and circle around with him when he's done. Go ahead.
Okay, thanks for the introduction. So our paper is entitled MMB, Flexible High-Speed User Space Middle Boxes. So I'll start with a bit of context. At first, there was the end-to-end internet where Alice and Bob could exchange packets while being unsure that they would remain untouched in transit. Then middle boxes happened, and now packet exchange by Alice and Bob are crossing various types of middle boxes, from network address translators to various kinds of tunnels, firewalls, TCP accelerators, and so on and so forth. So originally, most of those middle box appliances were implemented into dedicated hardware, but with the rise of virtualization and containerization, there's more incentives in being able to do it on commodity hardware. So the straightforward way to do it would be to rely on the kernel packet processing functions, but unfortunately it was shown to be a bit too slow to sustain high-speed packet processing. Plus it is missing a lot of potential optimizations, such as packet batching or more efficient use of caching and many more. Then one might ask, why not do it in user space directly? Well, first and foremost, because there's no direct access to the network controller. You have to go through a system call, which involves a context switch, which involves an extra overhead that we just can't afford. Plus, it relies on the SKBuf structure to store packets, which is very complex and it's not really in line with packet batching or batch processing. But fortunately, there is DPDK, which can be understood as a user space friendly driver for the network controller. which will write packets on memory regions shared between the kernel and the user space and allow user space to access the packet directly. Plus, it relies on a special data structure that are specially crafted to handle packet batching. So this opens the way for user space middle boxes and for adding more optimization and flexibility to it. So this is a short state of the art of existing kernel bypass framework. First, there is Click, which is one of the first to introduce modularity in the form of click elements, which are sets of related packet processing functions that the user should combine together to create its own packet processing pipeline. But it is kind of old and it's not much optimized. Then there is PF-Ring, which I'm not improving the performance of packet capture, but this is too narrowed for us. Then there is route bricks, which is the first step in extending Click to optimize it, to introduce parallelism support to it. There's also packet shader, but it relies on a GPU, which is out of scope for us. Then there is double click, fast click, and middle click, which are successive extensions of Click, which each introduces new optimization techniques. There is notably Click NP, which is the fastest here, but it relies on FPGAs, which are out of scope once again. And then finally, there is VPP, which is modular, inspired by Click, but not an extension of it, which has support for a lot of optimization techniques and runs on commodity hardware. So it stands for vector packet processing. It relies on DPDK, but it's not a requirement. There are alternatives. It has support for RSS, zero copy forwarding, and many more. It relies on the packet vectors paradigms. So it has native support for packet batching. And it has a node-based approach similar to Click. And additionally, it gives special attention to low-level optimizations, such as caching and pipelining. So this is an example of an out-of-the-book example of a VPP Dual-Loop. So it processes packet 0 and 1 in one iteration of the loop, but it starts by prefetching packet 2 and 3. So not only will it subtract the processing time of packet 0 and 1 to the memory access time of packet 2 and 3, but given the packet vector paradigm, the node-based architecture, and the nature of the CPU cache, it will in fact amortize the cost of memory access to the entire packet vector. And knowing that memory access is a major bottleneck in software, this is a major improvement. Plus, it processes two packets at a time, and this is done to leverage more hardware pipelining, which is basically anticipating the next instructions, and unpredictable jumps makes pipelining lose a few clock cycles. So by explicitly unrolling the loop, you can avoid losing clock cycles needlessly. And the last loop is simply processing the remaining packets. So we choose to rely on VPP to implement MMB, which is a middle box plugin for VPP, which has the following goals. It should be able to handle various middle box policies, from firewalls, network address translators, or more complex traffic engineering policies. It should be fast, even with tens of thousands, 100,000 rules. And it should have, if possible, an intuitive CLI. So this is an overview of the grammar for rules addition. You can add stateless or stateful rules. You can match on any combination of fields. And you can apply any combination of actions from modification, addition, stripping, mapping, shuffling, and dropping. So those are the two MMB nodes in the VPP forwarding graph. So we fetch a packet into the classification node, and then depending on the outcome of the classification, we forward packets either to the error drop node, to the rewrite node if needed, or to the next node in the VPP graph, which is IP4 lookup. And we rely on binary operations to perform classification and rewriting. Plus, we rely on a mask-based approach, which means that we do not consider single fields, but rather a combination of fields to reduce the complexity. So this is an overview of the processing path of the plugin. So we fetch a packet vector. We test each packet against each table. There is one table per mask, which contains all keys for the rules of using this mask. Then we test them against the more complex matching rules, for example, TCP options, which cannot be done using masks. And finally, we test the packets against the connection table. And if needed, we update the states of the flows. And when needed, the packet vector is forwarded to the rewrite node. The simple rewrites are done in constant time, and then the more complex one, the TCP options again, are done afterwards. So we compared the performance of MMB to 3 state-of-the-art solutions. FastClick, already introduced. It's an extension of Click designed to be fast. Then there is Express Data Pass, XDP, which is an in-kernel solution that relies on extended BPF, which allows to do packet classification in the kernel, and it also adds support for flow tracking tables, hash maps, and it's supposed to be fast, and IP tables for completeness. So we configured our testbed into 4 setups: direct, indirect, PCI pass-through, and a bridge setup. The direct setup is simply the 2 traffic generators directly connected to evaluate the bottlenecks and the baselines. The indirect setup with the frameworks running in bare metal on a device under test. Then the PCI pass-through setup with the frameworks running on a virtual machine with the physical network controller directly plugged into the VM with as few virtualization steps as possible using so-called PCI pass-through technologies. And finally, a bridge setup with a virtual network controller plugged into the VM, connected to the physical ones using bridge networks. For the sake of this presentation, I will skip the 2 last, but you can find more information in the paper or the extended version of the paper. So first, we evaluated the baselines of packet forwarding and found that VPP FastClick and kernel 4.15 is able to sustain most of the direct baseline. Then we evaluated the performances of 5-tuple firewall filtering by injecting stateless rules matching on randomly generated 5-tuples and measuring the throughput. We find that MMB and XDP sustains the direct baseline. Surprisingly, FastClick doesn't, because there are performance issues in one of the components. And surprisingly, IP tables on kernel 4.15 sustain the direct baseline for up to 1K rules. Then we evaluated a scenario of stateful flow matching, where we inject similarly stateful rules matching on randomly generated 5-tuple, but here we make sure that each flow matches at least one rule so that the states of each flow is maintained. The results are pretty similar. We find that MMB and XDP sustains the direct baseline. FastClick this time sustains 85% of the direct baseline, and IP tables behave similarly to the stateless scenario. And finally, we tested the TCP option parsing scenario where we matches on randomly generated TCP option kinds. It is not applicable to IP tables nor FastClick because FastClick doesn't support it, and we couldn't manage to push it into XDP in a modular enough way. This is probably possible, but not comparable to MMB. So we only evaluated MMB here, and we found that it is stable with up to 78 different TCP options, which realistically is fairly enough. So in conclusion, we evaluated MMB, found that it was able to sustain line rate for different use cases of middle box policies. In the future, we would like to add payload reconstruction to it to be able to implement policies for RPSs, IDSs, or other things. So if you're interested or just curious, just check out the repository. Thank you.
Great. Thank you, Korian. Questions? Can't tell whether you're headed out or to the mic. Here comes somebody.
Hi, Tom Herbert. So some of this actually ties in with a presentation we're doing tomorrow on deep dive into NICs. We're definitely going to have smart NICs coming that can do a lot of this processing inside the NIC. So I think a direction for something like this might be how to leverage some of those advanced features. Because we know once you start pushing stuff down into the NIC, like the firewall rules, they'll perform better. So something to consider.
Mm-hmm. Thank you.
Anybody else? Great. Let's thank Courtney again. Thank you. Glad your machine lasted. There you go. So, how you doing? Good? So, last talk of this session is checking in on network functions by Zishan Lakhani and Heather Miller at Carnegie Mellon. So, Zishan's a first-year student, a PhD in CMU's Institute of Software Engineering Research, and working on programming languages and systems research, and also does some work for Comcast around edge computing and programmable networks, and claims he's not on the job market, so no poaching, please.
All right, you all hear me all right? Cool. So this is some interesting work that we've been looking at. I've been looking at actually from two kind of ways, kind of inspired by work we're doing at Comcast around edge computing, and it's good the last talk was before me, so remember all those things about middle boxes and network functions, and about things like VPP. We use something different, and I'll talk about that. But we were doing all this work with IPv6, segment routing, variable data, and that kind of changed the way we thought about things. So in my research mind, I thought, well, how can I apply programming languages and software engineering research and tooling to doing these network functions? So kind of covering the last talk, network functions had this kind of vendor-based hardware items that ran these very single specific pieces of that ran in network, firewalls, IDS, load balancers. And then things kind of got recycled as we moved into the cloud and software. And so the way we thought about running these things, we ran them on nodes. There's really good work from people like Justine Sherry while she was at Berkeley, talking about how middle boxes have moved into the cloud. I mean, you see these things running in AWS now and all these kind of cloud providers. What we're really interested in, though, is the rise of how we're writing and modeling network functions, which is something probably maybe not everyone's interested in. I love higher level languages. I love functional programming. These were not the typical things I saw when I started writing network functions. But then there actually is a lot out there. So there are things like Pyretic, which comes out of the frenetic kind of lineage, which is a Python-based library for writing modular network functions. There's stuff like Slick that came out that lets you do interesting kind of pipelining for subsets of traffic. And then there's things like Netcat, which is this really cool semantic model for thinking about networks. It has proofs for soundness and completion. It seems really, really great and lets you do things like reachability analysis right in your code. For all these things that are really great, things are getting more and more complex. And even though you have these this great set of research that's coming out showing us how we can do certain things, it doesn't really cover a lot of ad hoc and kind of large scale ideas. Because now writing network functions is, is dealing with complex routing and load balancing policies. So my work at Comcast, this is the kind of inspiration and impetus for us, like what we looked at from there. Traffic monitoring is a major thing. You have a lot around experimental and new specifications, protocols, and headers. And then you have a lot of work. There's a recent, I think 2018 or 17, this paper called In-Network Computation is a Dumb Idea Whose Time Has Come. It's a great title. Talks about how they're doing aggregation and doing all these different kinds of views on computation in the network. So things are getting really complex. Can these frameworks that we have to write high-level code and network functions and packet processing, are we going in the right direction? So the motivation for us was, it sounds a little cheeky, because I come from web programming and application programming, was if I program in React, who here knows React, the JavaScript framework? Man, I'm definitely at a networking conference. But, React is this major kind of JavaScript UI framework that's gotten a lot of popularity because it's a really great set of engineering work. It does really smart work about doing differentiation and moving toward immutability and how we write programs. But if I'm a React programmer, how do I write a network function if I don't know much about the lower layers and packet level computation that's available? And so say I start and I have a way to do that in these high level frameworks, maybe in like a language like Python, as we saw. How do we know what we're doing is right? I don't know much about this. This is not my background. I don't read IETF specs all the time. How do I do this? And then how can we iterate upon this and debug and kind of learn as we're writing? And so this might be scary for some, but maybe it's okay if all those React and JavaScript programmers start coming over to write network code. Maybe. The problem that is out there with what's available in these higher level abstractions is that there's limits of correctness. So Netcat, which is, again, this really great semantic model for doing network programming. It's gotten better, and I'm basing this a little bit off the original work. They compiled down to code that had to work on the OpenFlow protocol. Again, that's great, but there's a lot of other protocols, of course, and even the original impetus of OpenFlow was like on-campus research and experimentation. And yet, if a new protocol comes in or experimental protocol is available, OpenFlow might not support it. And a lot of the case that I dealt with in coming up with this research was dealing with arbitrary ad hoc logic and variable linked data, extension headers, extension headers, extension headers. So we do a lot of work at Comcast around segment routing. Other than there was some libraries that had implemented versions of the V6 segment routing header, there was not much. We had to write a lot of this ourselves. And then just imagine when you have multiple extension headers on top of each other. We're not just talking, it can get pretty complex. And so dealing with how, if I update segments on the fly in the middle of the network over and over again, how do I change the packet length all the time? How do I deal with dynamic information around failure and reconfiguration? Separately from the research kind of part of this, my work at Comcast is dealing with how do we make things like failure and load shedding a primitive for how we write programs. How anybody can write programs thinking about these things and policies at an application level. So the last talk mentioned a little bit about Click. Click is kind of de facto like really awesome in '99. Way to write code for doing packet processing pipelines, and it's still used. Eddie is awesome for a lot of things, but this is a piece of code that's still in there to do IPv6 validation. With this kind of go-to bad sync that a lot of other little pieces of code also go to bad if things are not right. And you see that we have this kind of hard-coded value. And in our paper, if you download it, there's even code, a more complex set of code maybe from Facebook on their network load balancer called Katran, which just came out. Open source, I guess, officially not too long ago. And they have a lot of code. It's seemingly really good results, but they, everything's based on constants, hard-coded numbers. I mean, maybe this is pretty common in networking land. It is not common when you think of higher-level programming abstractions. So the two examples we look at in the paper, which are kind of these variable ad hoc ones, is the MTU send to big response. So you have a client that has like a TCP packet. It's way too big. We have to do these sets of actions to then return it back, including changing the protocol to an ICMP v6 and the v6 variation, calculating checksum, swapping source and destination. How do we make sure that happens, especially if I'm writing this network function from the beginning? The other one, as I mentioned, is the IPv6 extension headers, which if you look at the spec right there, you have things like obviously the segment list can change over time, and you have this TLV, type length value objects, which can change, and again, it's variable information. Earlier talk was about NDP. We do a lot of NDP, which has these prefix options. Sometimes you'll get options on those packets. Sometimes you won't. We've seen this in practice, and that makes things very difficult. So we want a way to think about this from an abstraction level. And so, as you see there, V6. And so we thought about what is an interesting way to combine a hybrid set of checks, or what we call contracts in software engineering and programming language land. And the impetus kind of came from early things, the Eiffel programming language, which was in the, I think, 86. Talked about this idea of design by contract, where you're focused on how runtime contracts would be turned on for monitoring and testing situations, and quoted from, I think, the original paper or book, you can just sit back and watch your contracts be violated. Again, this is during the design and testing phase of writing programs. And this is built into the language. These are contracts are primitive in Eiffel. And now you're seeing this in a lot of other languages. If you like some kind of modern Lisp, you'll see this a lot too. And so in design by contract, you can run this stuff in development, but like in our case, in our tool, in our prototype, we erase this information, these assertions, and work in release binaries. We also wanted to add some sort of static checking that is based on compile time assertions. So in languages like C, C++, and D, you'll see this used, and you can do checks on const and statics, which again happen at compile time. And these can actually remain in release binaries because they have their only effect is the static point of programming. And then we have this idea of static order preserving headers. So in the framework we use, my next slide's on the implementation. It's the one called NetBricks. It has this concept of the previous header as a type. So we use this kind of previous set of headers to determine order. So if you're traversing a packet in your network function code and you use something that's, TCP coming after not coming after a V6 or V4 IP part of your packet, that will be a compile time error. So we use that to our advantage in doing our code. So again, design by contract, as I mentioned, influenced by Tony Hoare and this work around Hoare logic, around pre and post conditions. We kind of relate that in our code to input and egress for pre and output and egress for post. Static assertions, as I mentioned, kind of comes from this world of C and C++, can do a lot of interesting work with checking on coercions as well. And an example we use it for is some of these MTU values for determining where something is too big depending on where you are in the packet. That depends on how many bytes you're actually looking at. And again, static order preserving headers is the idea of a statically defined order mechanism. And I'll show an example of what that means. So our implementation is done as a gradual extension to NetBricks, which is a DPDK-based user space that we just heard about take on this work, and it's written in Rust, which is a really cool language that is now starting to get, even Congress knows about Rust nightlies, if you saw a recent video. And in particular, NetBricks is focused on the idea of zero-copy soft isolation, and it's able to eliminate the need for copying packets, copying packets because of this idea of using static types to do these checks and using this idea of order. We just leverage it and go a little bit further. And we implement our work, our prototype, as a small Rust library, which generates code for validations and assertions. So the key here, and this comes more from some previous software engineering research and programming language work, is that we didn't want the programmer to have to write all these validations and worry about how all these validations work together. We let them write very simple checks, and we generate the code to do the work using macros. Another talk for another time about how great macros are. It's my favorite thing in the world. And Rust has hygienic procedural macros, which are really cool for a low-level, no GC language. So here's a NetBricks typical example, actually from newer code we've been writing, and a fork of NetBricks, which is open source in GitHub, and I'll talk. Yeah, you can find that in the paper. So this is a simple max swap where we're doing a simple parse here, and you see that we have these types like Ethernet that we can determine, and the code looks like a declarative map reduce. If you're familiar with Spark or any of these frameworks, that's the thing that NetBricks has, but it's very ad hoc. I can do terrible things. I can try to log do a log that's a blocking process as my packets are being processed. I have to know what I'm doing and think about it. So there's a price you pay. So our work in particular, let's see if this works. There we go. Yeah, a little bit delayed, but all right. Okay. All right. So I missed the word gradual. So we have these network functions. They look like this. I've allotted some work of filters, maps, and group bys that you can do in this. But what's cool about our work is that you can add this check attribute. We will check this. We will be able to check that network function. If you're composing these functions, for example, if you don't put the check, we won't check it. Again, it's gradual. It's buy-in, and we can take old network functions, for example, and just add our code onto it. And if you don't want it, you don't get it. And so in our piece, we have our preconditions here, which are using a macro called ingress check, where we can determine, we're actually saying, here's the order we expect, which again is going to be static time, runtime checks, and then a post condition, which checks what the packet was before to what it is at the end. And so again, order is checked statically via trace or packet contents. We have pre-checks that validate incoming content and store content at runtime. And we have post-checks that validate the transformed packet is correct. In this case, when I have an MTU send too big, I have a TCP packet, for example, that's too large. My return packet now should be an ICMP packet that is the right amount of bytes, 1280 in most cases, that is the right amount of bytes. And I have swapped destination and source addresses. I have swapped Ethernet addresses. And basically, this works, again, at design time and runtime. So our evaluation was pretty much looking at additional syntax, compilation time, and runtime overhead. Again, the focus has been on the design phase. So we look at syntax added. This is a very common software engineering thing you see in papers. Admittingly, I will say I kind of hate it, but I did it. And so we see that we don't really add many lines of code. Most of it really around configuration for adding some new libraries. But adding these checks is basically n to the amount of checks that you want to add for assertions. This one we feel is pretty important, which is that we have this tool. The goal is design by contract, combining static and dynamic checks. But compilation time should not be affected. The same Rust program, the same netbricks function you should be writing without any of these generated code should be the same as with or without. So we show that actually in some cases there's no significance. We're actually faster. It means it just doesn't matter. And there is a runtime cost. So we're doing some work to do like order preserving headers. We're actually tracing the entire transformation of the packet header by header to make sure that in the code that we generated to make sure that the order is correct, for example. And we do a lot of runtime storing for the dynamic check. So as a packet comes in, we store all this information so we can use it for validation at the post condition. That does take time. So we have these runtime checks. Also, we're not using the most optimized data structure. But again, this is for design phase. And ideally, you wouldn't be running this in production. You would only have the static assertions in production. So our future work, we've already started on some of this, is not just to run this kind of on your computer while you're designing programs and network functions. You can do this as part of a deployment model in CI, or already we have this running up in Mininet and ContainerNet, which we use heavily to run this up. You can run these as part of your simulation. We hope to further leverage static analysis of input programs, and we really want to bring in a lot of the work that we see in compilation now and even from UI tooling around interactive feedback, program slicing, and refinement using program refinement and constraint solving. So there's a lot of work in P4, which is used to write a lot of network functions to look at constraint solvers for work, but they tend not to go for these very ad hoc variable link data examples, and we hope to actually show those. In practice, at Comcast, we use this netbricks library, and we've forked it and created kind of our own version. We've rewritten a lot of the runtime. We do use some of the checking work that actually I've done in my research, but we also had to come up with some new ideas that kind of emphasize what does it mean to program these network functions for anybody, and we have to create limitations. So one of the limitations we have to do is this idea of scope side effects. So I mentioned earlier in the MTU example, we have to update all these things when you change to go back to the sender with the specific response. We basically have this cascade function, which says anytime that I update parts of the packet, automatically cascade and change the packet length and recalculate the checksum. The same thing for segments. So the work we do in Comcast, we're constantly changing semantics on the segments. We actually use the bits in the 128-bit addresses to actually encode actions. Takes an idea from an old idea called active networks. And so what we need to do there is say, well, when I set the segments, make sure I change the packet length, update the checksum, et cetera, et cetera. Let's not let the programmer have to actually do that. Let's force them to do that. It's a limitation up front, giving away some interesting flexibility. But interesting things. We also have this concept of type packets. So not only do we have the previous header and the header that comes after us, we can actually say what's the envelope. So we can bound things using our type system to say, well, a TCP or UDP part of the packet, can't come after some ICMP one. And we can now do that using bounding in types. And again, that's statically checked. So the takeaways are, we need better approaches to verify and interact with network functions and processing packet processing program properties. In this work, we have a hybrid approach that we use to gradually check and validate arbitrary logic and side effects. And by combining these different kinds of contracts, we show that a mixed model can really work. And we did this all without penalizing the developer and programmers at the design time of writing these network functions. Thanks.
Great. Thank you. Questions?
Hi, I'm Dirk Kutscher. Really cool work and a nice presentation. It's probably in the paper, which I haven't read yet, but I assume this supports stateful functions as well.
Yeah. I mean, so the work that we actually use NetBricks for is doing a lot of stateful functions, so it does,
okay,
yeah.
Okay.
Yeah.
Are you aware of the computing in the network research group in the IRTF?
I'm aware of it, yeah.
Okay.
Yeah, for sure. Yeah, so, yeah, I mean, I hope to see more of this. Most of my background came from looking at stuff like Netcat, which you won't necessarily always see here, you'll see at Popple. I was so surprised when we started working in networks and going, not everybody's using Netcat? And everyone laughed at me. And the work is so amazing, but the idea is, I think, obviously, for actual use, you have to find some sort of balance, and that's what we're trying to convey.
Okay. Yeah, thank you.
Anybody else? Great. So let's thank them one more time. And next session starts at 3:50 p.m. So enjoy your break. Yeah, you're good.